Hello everyone, welcome to another video lesson where today we will discuss the Poisson process and how we can simulate it and understand it better in Python. The Poisson process is a widely used counting process, and it's used when the only thing that we know about an event is the rate of occurrence of that event. So for instance, in an earthquake, we might not know when the earthquake will happen in a certain region, but we might know that it happens randomly at a certain rate. So for instance, 2 earthquakes per year. Okay, that's the rate. So we don't know any additional info, we just know that it happens randomly at that rate. For us to model this type of phenomena and to model, for instance, the number of failures over time, if it has a pattern that we only know the rate and nothing else, such as, for instance, in the life usage portion of the bathtub, we can use the Poisson process. But before we go into the Poisson process, let's see the Poisson distribution. So the Poisson distribution is very much connected to the Poisson process because it governs the random variables that the Poisson process uses. So, for instance, a Poisson distribution with parameter lambda can be defined such that x is a Poisson governed by the parameter lambda if its range is discrete. So we can only have the probability of x being equal to 0 or 1 or 2 or 3 or 4. So 0 failures, 1 failure, 2 failures, and so on. And the probability mass function, because we're talking about a discrete random variable, remember that we have to use the probability mass function, is given by a certain expression such as this. Interestingly, if x is a Poisson, then the expected value of x is lambda as well as the variance of x. So now let's try to check the Poisson random variable and what we can do with it. So now in the Python environment, I have here my libraries that I have already imported, and I'm gonna generate a Poisson distributed events. Okay, so the first thing that I'm going to do is I'm going to select a mean. So I'm going to say my mean of occurrence of events equals 3 per year. Okay, and now I can call my Poisson random variables. I'm going to say that the mean, the parameter of the lambda, in this case called mu, equals 3, and the sample size, how many events I'm going to generate, will be 1000. The best thing would be to put a variable with this information, and then I'm going to keep this in an array, events, number of events per month. Okay, and then what I'm going to do is I'm going to print number of events per month, the first 10, because they're going to be 1000, but we're just going to print the first 10. So let's check. And we have, for instance, in the first month we had 1 event, in the second month we have 2 events, in the second we had 4, 3, and so on. Okay, but now I want to calculate the actual mean So I'm going to say, I'm going to calculate the mean number of events per month as the mean number of events per month. I'm going to print. Mean of Poisson. I'm going to print the variance also. And you might guess what number I'm going to get. Okay. In this case will be the variance. So let's check. So you have 3 and 3, which is according, of course, this is only with empirical data, so the numbers will not be exact equal to 3, because we're dealing with some uncertainty. But the idea is that because the lambda is 3, the mean and the variance will be equal to lambda. So we can now look at other problems, such as, for instance, if you knew that the equipment had 3 failures per year on average, so you knew the lambda, and then you want to know the probability that they will have 5 failures on a given time. So what you could do here is you can do it empirically. So you could go to the number of 5 events per month, and then you go to your data, number of events per month, and you equate it to 5. And then you know that the probability, or the estimated probability of having 5 events per month equals the number of events per month over the number of events per month, and then you print probability of 5 events per month. Okay, let's check. I have to calculate the numbers, so count non-zero, or the length. I could also do the length. And I get 0.094 probability, so around 9% probability having 5 events. If we put, for instance, 3, we will have a higher probability. So a higher probability here of around 24%. But we can also resort to the theoretical function. So we can go to Poisson.pmf. We say that the k equals to 3 and the mu equals to 3. And I will get the probability, so I can print it. Because I'm indexing my probability mass function on the number of failures equal to 3, given that the average number of failures is 3. And I get more or less the same probability, but this was estimated from data, and this is estimated from the theoretical calculations. If I want to create a probability mass function, I can also do it theoretically. So now I can create the probability mass function theoretically or not. We will start with the theoretical and see if they match. So the first thing that I'm going to do is for k in range 10, I'm gonna PLT line from K on K, epsilon min equals 0, epsilon max equals this probability here, but on K. Okay, so let's see. But I could do the same with my data, right? So my data also has a mu of 3, so the number of events per month. And I can calculate this. So this plot and this plot are more or less the same, given that we are dealing with 1000 events of sample size. So what if we had other questions to ask, such as, for instance, we knew that a certain equipment breaks 15 times per month on average. What is the probability that this equipment breaks more than 15 times in a month? Okay, so this is a little bit different. And if you remember the cumulative distribution function, which was a failure function, the idea is exactly the same. So what I'm going to do is I'm going to calculate the probability of more than 15 events per month. Okay? And this probability equals the Poisson C cumulative distribution function at 15 with a mu of 3, and we want to know more than 15. So this calculates the probability until 15. So we have to calculate 1 minus this probability to get the probability that we really want. Okay, and then we can print the probability. We can also estimate it empirically. I'm not going to do it, but it's really easy just to count the number of times that you have more than 15 events per month, and then divided by the number of total events. But theoretically, this is going to be, the actual name is CDF in small. Okay. Oh, yeah, that's because my mu was 3 and it should be 15. So actually a considerable probability. So another thing that is important to know is that if you have the counting process being identified by the Poisson the distribution, it can also be characterized by the exponential distribution, because it can be shown that if nt is a Poisson process with rate lambda, then the inter-arrival times, the local times, will be independent and will follow an exponential with lambda. We also have the global times that we have already talked about, and the time of 1 equals x of 1, but the time of 2 equals x of 1 plus x of 2, and the time of 3 x of 1 plus x of 2 plus x of 3, so and so on. The time of n equals a gamma of n lambda. So each random variable t of n, t of 1, t of 2, t of 3, will follow the distribution gamma with also the lambda parameter and n. In that case, the expectation in the variance is a little bit different, but also dependent on n and lambda. So what we are going to do is to create an exponential random variables that has as the scale equals to 1/3 and the size equals our sample size. And this is going to generate local times. So let's see. Okay, so we have here the local times. Because you said that the scale equals to this parameter, which is the inverse of the lambda, you might be confused by this, but this is how in Python it works, because it has a different definition of lambda. So you always have to pass 1 over lambda in this case. And here you have the values that if you average them, and then multiply by the lambda, you get approximately 1. Okay, and it's approximately 1. Why so? Because the local times would be distributed in a way that you have 3 events on average. Okay, so that's why I multiplied by 3. Finally, we also have the gamma distribution of global times. We can simulate, for example, for the second failure, the different global times that for different equipment would happen. And we generate it, and we can calculate the mean and the variance. Okay, and interestingly, the exponential had a variance of 0.10. We have here the double, because we're talking about the second failure. And the inter-arrival times, the first inter-arrival time is equals to the first global time. And we have here the mean, so the mean global time, that is approximately the double of this one. So far so good. So if we want to simulate the whole thing in one go, we could do something like this. So we define our lambda, our number of events, we have 2 with the event times, the inter-arrivals and the occurrence times, and the event time starting at 0. And for each event that you want to generate, you generate a random probability. You calculate this in a different way that we have seen, but basically it's an inter-arrival time. And to calculate the global time, you just add one to another to make sure that they make sense together. And by this way, you can calculate the number of failure times, the distribution of inter-arrival times, and the global times that are connected to the inter-arrival times.